Folks, we're going to need to put everything away except our notebooks, our pencils, and our reference tables. Yeah.
So she got more like the same questions that they can still answer the closest to.
That's a centimeter.
So mine is short, his was.
No, mine's different. Mine's over 8.
That's my mistake. Because a millimeter, when you look at a ruler, a millimeter is the space between the little itty bitty marks. It's not a pencil. If I had marked something wrong, that was correct.
That's why I was asking.
Yeah, you
Got your 5 points.
So I'll tell you, it made a difference of maybe a quarter of a point
Yeah,
on its average.
We basically got the same thing, actually.
I'm like, there's no way. There's no way. Like, if this stuff works,
All right, let's clear our desks of everything but your notebook, a pencil, and a reference table. We are starting Unit 6 now. Would like to do one of these? We're going to start Unit 6. Let's go! That was the bell. And I don't want you to have additional homework because I can't get through the material in the 40 minutes because you're not ready. What I'm handing out to you right now is your next packet for Unit 6. Please go ahead and put your name on top of that. We will not be using it today, so you can just put it away. We'll be using it again on Monday after your test. Tomorrow, you'll be taking a quiz on the notes I'm giving you today. So your assignment tonight, in addition to finishing the review, is studying. We don't need Chromebooks. We don't need our Unit 5 packets. You just need your pencil, your notebook, and your reference table. So pack everything else up, please, including your quarter exam. We're going to start Unit 6 today, which now is going to get us into an area of physics called mechanics, which is page 6 of our reference table, continuing with it. Now what we're going to do is talk about why the objects that we've been discussing that are moving, why they move the way they do. Bryce, can you put your test away, please? We don't need that out. And Josiah, put your Chromebook away, please. We don't need that out either. Just your notebook, your pencil, and your reference table, please. No calculators are needed for this. We're not going to learn how to do any mathematics. Today is straight vocab. 40 minutes of vocab. Yep. That's your quiz tomorrow, is on the vocabulary and the basic introduction to Newton's laws of motion. So we're going to start off by understanding what force is. That's what the rest of this entire course is about. Force. And what we're going to learn about today is what is a force. You should be able to find that. Basically, if a kindergartner asked you this question tomorrow, you should be able to tell them what it is. In words they would understand. Then we're going to talk about how we categorize different kinds of force. The first way we categorize them is by the interaction that's taking place between objects which are exerting forces on each other. There are 4 different types of interaction. You should be able to name them and describe what that interaction is coming from. Then we're going to talk about how objects can exert forces on each other, either through contact or acting over a distance. And I will ask you to name examples of forces that are in each category. So let's get started. What is a force? A force is any push or pull that an object experiences because of how it interacts with something else, another object. It's a push or pull that comes from an interaction with something else. So I'm going to demonstrate a force on this chair. I just pushed the chair. That's a force. This is a force because I'm pulling on the chair. Those are forces. They're pushes and pulls. What was the interaction I just demonstrated? It was between me and the chair. That's it. Those are the 2 objects that are interacting with each other to exert pushes and pulls on each other. Now, the symbol that we use to abbreviate all force in the entire course is a capital F. Capital F is the abbreviation for force. Now let's turn to page 6 of your reference table. And on page 6, we're going to check off that variable right here. Capital F represents force. Capital F represents force. Now, what we're about to learn is that forces like velocities, displacements, and accelerations are vectors. When you push something, you push in a direction. When you pull something, you do it in a direction. So because these are vectors, let's add our arrow over the top to remind us that there will be a direction on every force we work with. Now, in the metric system, all forces are measured in a unit named after Sir Isaac Newton, who was the first scientist to describe forces. So it's called a Newton. Notice that when I spell it out as a word, it's lowercase n. If you were to ever write it out, if you were to put a capital N, you would be referring to Sir Isaac himself. All right, so if I had 10 newtons of force and I wrote out 10, capital N-E-W-T-O-N-S, I would have 10 Sir Isaac Newton, 10 of him in the room. Okay, that's not what it is. When we name a force for a person and you spell it out, it's always lowercase in science. But when you abbreviate it, because it's named for a person, it's capitalized. So we want to make sure that the unit of force, when we write a Newton as an abbreviation, and that's how we always do it, we capitalize that capital N. So make sure here after force, we identify that unit as a capital N, a Newton. If you were to put a lowercase n, that means nano. It does not have the same meaning, so it would be marked wrong. Okay, they have different meanings, so you have to be precise about your upper versus a lowercase letter. Now, a Newton is a derived unit, and I know I just said it had to be lowercase. Where I got this from had an error. That should be a lowercase n, or you just write 1 capital N equals 1 kg times m over s squared. So a Newton is the same thing as a kilogram times a meter per second squared. It's what we call a derived unit. During one of our first lessons this year, we talked about the 3 fundamental measurements in physics, always being units of mass, length, and time. That's how we get every measurement in our measuring system for physics, with lengths, masses, and times, not forces, which means that the unit of force comes from units of mass, length, and time. And we can see that here. We know that a kilogram is the unit of mass. We know that meters is the unit of a length. And we know that seconds is a unit of time. And in fact, a meter per second squared is another derived unit. It is the unit of what? Acceleration. So this helps us understand what accelerations produce. When something is accelerating, it's because there is a force acting on it. And that explains the why, which we'll be talking about through the rest of this course. So as I already mentioned, forces are vectors, which means they're going to have not only a size, meaning how much you're pushing or pulling, but you're going to do it in a direction. Like when I push this chair right now, I just pushed it that way. There is the direction of that force. What we can see here in this diagram is that there are 3 forces acting on the wrecking ball on that crane right now. I draw them with arrows. So what I see here is that this rope is pulling the wrecking ball up and left. This rope is pulling that wrecking ball down and right. And then there is something else pulling it straight down. Those are individual forces, which we will be naming today. And then we will be learning in the rest of this unit how to come up with the sum of these different arrows. Very similar to how we looked at sums of arrows when we did displacement arrows or velocity arrows, drawing them head to tail with a ruler and protractor, and then finding their resultant, which is the net amount of force on the picture. Now, as I mentioned in the objectives to this lesson, you have to talk about the different kinds of interactions that objects may have between each other. What scientists learned back in the 17th and 18th century is that there were 4 basic types of interactions. Since the mid-1950s, this has been revised. So we're actually learning something that's out of date in this course, but this is what we have to work with. Scientists in the last 70 years have learned that 2 of the interactions are actually from the same thing. So they have now been linked together. And if you were to take a college class in physics, the professor would not talk about 4 different types. They would talk about 3 different kinds of interactions. Let's go through what the 4 used to be, and I'll tell you how they link in current understanding. So the first type of interaction comes from something called gravity. We've been talking about gravity a lot since we started discussing free fall, but we never really talked about where it comes from. Gravity comes from an interaction between objects that have mass. So anything that has mass, the mass creates gravity, specifically a gravitational force. And the type of interaction that objects with mass have is said to be attractive. Now, there's basically 2 ways forces can be exerted on objects. Either by attraction, or the opposite of attraction is repulsion. So what do I mean by attraction? Can you tell me? Something they talk about with you in middle school. What do they mean when objects attract? They what, Jacob? They come together. They're being pulled together. And what this interaction tells us is that objects with mass can only get pulled together. Gravity will never push them apart. That's why when you jump up, gravity with the earth is pulling you which way? Back towards the earth. The earth is never going to repel you because of gravity. If you're being repelled from the earth, something else is making that repulsion happen. Okay. Now, this is saying everything with mass exerts another attractive force on the other. So let's do a little thought experiment here. My pencil has mass, right? Because there are molecules inside of it. I also have mass. So based on this statement, what should be true about me and the pencil? What should be true? Nate, what should be true? The pencil has mass and I have mass. What does that statement say should be true between the pencil and I? We should be attracted to each other. I didn't see the pencil move towards me. Did you? What did it move towards? The earth. Why didn't we see the pencil move towards me? Has something to do with mass. Because the earth has more mass, which means that the earth exerts more gravitational force on this pencil than I do. This is why when we say that gravity is the weakest force, that it only becomes significantly measurable when one of the interacting objects is really massive, huge, like a planet. But it doesn't mean that there isn't gravity between me and the pencil. Let's say all of a sudden I was out in space where there was nothing else around me besides this pencil and me. That's it. No planets, no moons, no comets, no stars, no nothing. Just the pencil and me. Not even air molecules. Then if I release the pencil, what we would observe is that the pencil and I would float and accelerate towards each other. I would move towards the pencil and the pencil would move towards me because there would be no other mass around us to also pull us. But that is what is true about mass. Masses always attract, even if it's very weak. The second type of interaction is called the weak nuclear force. Do you see how the word nuclear is in parentheses? That means you don't have to write it. You could just say the weak force. The weak force and the weak nuclear force are synonymous. This is the category of force that exists entirely inside of the nucleus of an atom. Hence, that's why we include the word nuclear there, because it's inside the nucleus of an atom. And I know you studied nuclei of atoms in chemistry. We're going to refer back to that knowledge in this class. Now, what happens to some nuclei because of this interaction? Because of this interaction, which happens to be a little bit stronger than gravity, but not a lot stronger, what we end up seeing is that some nuclei, not all of them, will spontaneously decay. That's called radioactive decay. I know you studied that in chemistry. Every element from 83 on up on the periodic table has at least one naturally radioactive isotope. Element 83, in case you don't recall, is the element bismuth on the periodic table. It's one above lead, which is 82. Once you get to bismuth on the periodic table, the nucleus is now sufficiently large enough that the protons repelling each other is enough force to make that nucleus split apart by itself. You don't have to do anything to it. It just automatically happens, releasing beta particles, positrons, and gamma radiation through radioactive decay. And that happens with a half-life. So if a half-life is 12 minutes, what we see is that half the mass will disappear in 12 minutes. And then another 12 minutes later, another half is gone, and so on and so forth. You remember learning about that in chemistry? That's what we're talking about. That all happens because of this interaction. This interaction, scientists have learned, is actually now in the same category as number 3, which is called the electromagnetic interaction. The electromagnetic interaction is a type of interaction that comes from a property that everything has called electric charge. Charge can either be positive or negative or neutral. based upon the type of charge that a particle has, will determine how this interaction occurs. This interaction is much larger than gravity. And in fact, when you have an object that is both massive and charged, the charge interaction takes precedence because it's about 1 billion times stronger than the force from the mass. The last interaction is the strongest one, called the strong nuclear force. You need me to go back here, Shane? So 2 and 3, weak nuclear and electromagnetic, are now linked. They are said to actually be the same interaction. In classical physics, prior to 1950, they were separate. But now, since we've learned, they are actually the same thing. The fourth interaction, as I mentioned, is called the strong nuclear force. Again, we see the word nuclear is in parentheses, which means that you don't have to write it. You can say the strong force instead of strong nuclear force. They're synonymous. But you can't write nuclear force. Why can't you say nuclear force? There's an obvious reason. Shane? Yeah, because then we don't know which nuclear force it is. Is it the strong one or the weak one? Now, what is this force responsible for? It is the force that's responsible for the actual creation of a nucleus in an atom. It's the interaction between protons and neutrons inside the nucleus of an atom, which glues those particles together. And if you remember from chemistry, that is a very, very, very strong interaction. That's why we call it the strong force. It is the strongest interaction we know of. And this is why when we try to break the nucleus of an atom apart, like we do with fission and fusion nuclear reactions, we get enormous amounts of energy. Amounts of energy come outing of the nucleus. One nuclear particle, not spontaneously, but being forced apart, being smashed apart, produces an atomic bomb, or can create the energy in a nuclear reactor. And this is how we're going to end the course, by learning all about that force. That is the last force we're going to learn a lot about. And that was all described by Albert Einstein. He is the one who was able to explain this force, the strong nuclear force. Now, the one thing we have learned about is that the strong nuclear force is what we call a short range force. That means it can only interact, it's the only interaction between particles when they are super close together. Specifically, when the particles that are interacting are less than a nuclear distance apart. This is why when a nucleus gets to be really big, like bismuth, number 83, with 83 protons and some number of neutrons, it will be too large, and then the protons will start repelling each other. That electromagnetic interaction takes over. All right, so let's now talk about how objects can exert forces on each other. They can do it in one of two ways. One is through contact. If an object must exert a force and can only exert a force on something else through direct touch, that's called a contact force. So if I wanted to exert a force on the chair, I actually have to touch the chair to push it. That is what we mean by a contact force, when things must physically touch together. The other way forces can be exerted, and only some forces can work this way, is over a distance. We call that action at a distance. If the two interacting objects don't necessarily have to touch, and they can still push or pull on each other through separation, they are classified as an action at a distance. That would be like me looking at that chair and doing this and expecting that chair to move. That doesn't happen, right? That's fiction, science fiction. Harry Potter can do that with his wand to make the chair move. I can't do that. I cannot exert forces at a distance. But Let's see if you can name the most common one that can. Yeah, the earth does not need to touch my pencil in order to pull it. That's why we would say gravity is an action at a distance force. Let me show you another one that I know you have familiarity with. What do I have here? Two magnets. Do these magnets have to touch to push or pull on each other? Well, let's find out. Did they touch initially? Are they? No, that one jumped up and reached the other, which means that magnetic forces are also action at a distance. Magnets don't have to touch to push or pull on each other. Oh, geez. I remember when my daughter was young, same age as you guys. She had those little Thomas trains that had the little magnets on the end, and they would stick together because of the magnets. The train, do you know what I'm talking about? Okay. Yeah, it's the same idea. Magnets work that way. All right. Now, I'm going to give you a chart here. I'm going to give you a minute to copy it down. And this describes all of the individual forces that we're going to be talking about this year in terms of forces that can act. So it's a chart which tells us the name of forces that have to act through direct contact, or the names of forces that can act over separated distance. Notice that I'm giving you the name of the force, and then I follow it with an abbreviation that we're going to use for these forces all year. I will never, ever, ever again write out the name of the force. I will only use the abbreviation from today on. So I'll give you a minute to get those all copied down. You can see that there are 6 forces that act through direct contact specifically, and then 3 that we've already talked about, which are action at a distance. And what I'm going to do for the rest of the period is go through those 9 forces to make sure you understand when they occur. In terms of the text after this, I don't know that you need to copy down everything I'm going to put up on the slides for you. If you want all of the text, you can certainly go to our Google Classroom later, pull up the slides, and look at all of the text and get it written down. But it's more important that you understand where these forces are and what they come from. So when I refer to a normal force, what is that I'm referring to? And that's what we'll spend the rest of today talking about. And that will conclude our presentation after I get through all 9 of those. So I have 9 more slides after this. 1 for each. I don't know. It just is. It has something to do with Latin. One of the first is we're force learned about. I think B has something to do with, in Latin, with magnets. All right, can I go on? Everybody has the chart copied down. Now, like I said, do you need to copy all of the text down after this? No. You got to really pay attention, maybe write one statement for each force so that way you know what that force is referring to. Okay, so let's start with the applied force, whose abbreviation is F, and then the subscript APP. When we're talking about an applied force, this is the force of a person pushing something. So when I push the chair, we call that an applied force. My force on the chair is an applied force. Okay? The force between a person and some object is an applied force. All right? The force of a person is the applied force. Next, gravity. The symbol for that is Fg. This one we already talked about. Where does this come from? It's a force between objects with mass. That's exactly right. It's an attractive force exclusively. We already have that from earlier when we talked about the gravitational interaction. Now, what you need to know is that sometimes we also call this your weight. Your weight comes from the force of gravity between you and the earth. It's the earth pulling on you and your mass, which gives you your weight. And as you know, everything here on Earth has a force of gravity directed straight down towards the center of Earth. We've already talked about that in our previous units. All right, let's go to the third one. Normal force. This one's a little tricky. Normal force is Fn. That's not tricky. What's tricky is what it is. It's a force of support that gets exerted on objects when they are in contact with another surface, another object. And it's always perpendicular to the surface. Always, 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 always. So let me just explain what this means. And I'm going to go to my document camera so that way you've got some pictures in your notes to help you with this. Because normal forces are always exerted by a surface that an object is in contact with, and it must always be perpendicular to that contacting surface. So let me show you what that means. Let's say I have a table here. There's a table. I'll put the legs on the table here, and this is the floor. Let's say I put a box on the table. The table is going to push up on the bottom surface of the box. This is what we call the normal force. It's the force of the table surface being exerted on the bottom surface of the box, and it must be perpendicular to that surface. Which means that if I were to now take that table and angle it like this, and keep the box there, then the table is now going to push on it that way. That would now be the normal force, so it maintains its perpendicular nature with the surface. In mathematics and physics terms, the word normal always means perpendicular. So anytime I say something is normal, it means it's perpendicular. They're synonyms. So the normal force is a perpendicular force. Perpendicular to what? The surface where the things are touching. Okay? Let's now talk about the friction force. A friction force is symbolized as FF. You already have that in the table. Where does friction come from? It comes from surfaces that are rough at the microscopic level trying to slide across each other. So this is another force from surfaces that are in contact as objects try to move across each other. Do objects actually have to move for there to be friction? No. Let me give you an example. Let's say I have a box which weighs 300 pounds. And it's right here in the middle of the room on the floor. I can push it. I'm pushing this table right now, but it's not moving. Why isn't it moving? Because there's friction opposing my push. So just because things are not moving doesn't mean there isn't friction. It's a different type of friction. There's multiple types of friction, which we'll be talking about later in this unit. And it always opposes the motion of objects or attempted motion, and it's always parallel to the surface. Unlike normal forces, which are always perpendicular, friction must always be parallel to the surface. It must always be parallel to the surface. Okay? Can I go on? All right, let's talk about air resistance. Air resistance, F air, sometimes called the drag force. You might hear it referred to as that, F drag, F air. They mean the same thing. It's a special type of friction that comes from objects trying to move through the air, from the air molecules pushing against. This always opposes actual motion of objects in the air. And as we talked about when we started studying free fall back in Unit 4, this is often going to be ignored or neglected because it's usually small. Remember, it only becomes significant when objects are moving really, 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 really fast, or they have large surface areas. Do you remember that demo I did with you in class with the piece of paper and then I crumpled it up? We saw how surface area plays a direct role with the amount of air resistance objects will experience. We're not really going to talk very much about air resistance. As I said, we're usually going to ignore it. And what you need to know about air resistance, we've already talked about in our last couple of units. Tension force is Ft. This is the force in a rope, a string, or a wire. When you pull it taut, and then what we get are forces that are equal in size on each end of the rope. So in this picture, which is tug of war, this rope is taut. There is a tension force pulling this way and another tension force in the rope pulling that way. And they're equal in size. Interestingly, think about this for a minute. Can you push something with a rope? No, that makes no sense, right? Try tying a rope to a box and pushing the box with that rope. It's not going to go anywhere. The only thing you can do with tension is pull. Tension must be a pull, not a push. All right, can I go on? The next is a spring force. This is a force in a spring, Fs. And it's a force from a spring when it gets compressed or stretched. So take a look at this spring here. This is a very large spring. If I stretch it, look at what happens when I release it. It goes back to its normal length. If I take the spring and I compress it and I release it, the spring goes back to its normal length. That force, which is trying to make the spring go back to its normal or equilibrium length, is called the spring force, Fs. So when you're reading a problem and you hear that there is a spring in it, you should be thinking spring force, Fs. The next is electrical force. There's this one and one more. The electrical force, Fe, is what we're going to be studying starting in Unit 11. This is the force between protons and electrons in atoms. That's all I'm going to tell you about it now. I'll tell you more about it when we get to Unit 11 this year, and we spend Units 11, 12, and 13 studying this. And then the last one is the magnetic force. This is Fb. This is the force between north and south poles of magnets. And that's it. And we'll spend all of Unit 13 studying the magnetic force. Does anyone need me to go back to any other slides? Yes, Bryce, which one? Tension, you got spring. Here you go. They are posted in Google Classroom. Yep, for the entire unit. They posted this morning. Shane? Normal? We got a few minutes, so you don't have to pack up quite so quick. If you need to get text, I can pull it out for you now. Make sure you study these notes tonight. You do not get to use your notes on tomorrow's quiz. We're going to see how well you studied these notes. Anyone need any other slides? Okay. You also have to finish the review for tomorrow.